Okay, so let's start. So today's topic is going to be about classification. So this is one of the main topics in machine learning in general. We will be using vector space models, so the same things we have looked at, but this time we will use vector space models to represent classes. So last time we used vector space models to represent words, data objects, individual objects. This time we will look at how we can represent classes, a collection of things in a vector space model. And so since we're going to use vector space models again in this lecture, and this is, I thought maybe we can spend a few minutes first to review the things we introduced last week. And if you have any questions, if there are things that still are unclear for you, this is the time to ask. So we will assume that after this review that we are all on the same page and we understand what we mean by a vector space and dimensions and all these kind of things. So last week we talked about semantic spaces and we define a semantic space as a vector space model or vector space models for distributional semantics. And in distributional semantics, we explained this by the quote by Firth, "You shall know a word by the company it keeps." So we consider the meaning to be represented in through the context. So we represent words as points or vectors in a feature space. And the positioning of these points or these vectors is dependent on the co-occurrence counts for various context features. So when we looked at words, so in the obligatory assignment, you looked at 120 words, target words, and you took the features to be the co-occurrence or the co-occurring words within the same sentence, given a bag of word context. So for each word, what we do is we extract the context features from a corpus, like the Brown corpus. And then each feature type would correspond to a dimension in our space. So the dimensionality of the space is determined by the number of features we have. Again, and then the obligatory assignment, that was determined by the number of unique words that were observed as occurring features with the target words. And then more formally, each word OI, is represented by a sometimes length normalized, and we explained why we length normalize vectors, and an n-dimensional feature vector. So we have a feature with n components. Each of these components is corresponding to a feature that we observe. So a feature xij within this feature vector is or indicates how many times the word oi occurred with the feature j. So, and then we introduced measures like the Euclidean, and we said that we can compute the distance between words. Again, when we say words, then we're talking about feature vectors here. Within the space by computing Euclidean distance or proximity, spatial proximity by computing cosine similarity. And so the whole idea was that we can more or less approximate semantic relatedness through distributional similarity, through these distributional properties of words. And this again can be approximated through spatial proximity. So in this example here, we look at 4 words in a 3-dimensional space, and we have 3 features in this 3-dimensional space, which bake, share, and eat. And you can see immediately that a word like taxi is less similar to the other 3 words, because taxi can be, so it has a high value on the share dimension or the share feature, because you can share a taxi, but the rest also have this high value, but you can't eat or bake a taxi. Then when we move to cheese, we see that it has a high frequency or has some value on the dimensions share and eat, but less on bake. And then when we move here, we see that these are 2 similar words. So this is just a simple visualization of how we can look at at feature vectors and words in these feature vectors. And then towards the end of last lecture, we also looked at using vector space models for information retrieval and for finding documents with similar contents. And this is not an essential part in the course, but it's important to get an intuition of how this works, because the readings for this lecture and next lecture, maybe the one after, are from a book on information retrieval. So maybe some of the examples you encounter refer to documents being represented in a vector space. And the idea is simple. Each document is represented by a feature vector, and the features on this vector corresponds to the terms occurring within this document. And again, here we approximate, or we make an assumption that spatial distance corresponds to similarity of content. So documents that have smaller spatial distance are more likely to be similar in terms of content. And we can represent a query. So if we are thinking in terms of search engines, you can represent the query itself as a vector, like here, and then measure the relevance of documents that you want to return in your search interface in terms of proximity, again, in terms of the cosine measure, for example. So yeah, is this all clear? Do you have any questions on last lecture or things related to vector spaces? No? Okay. Well, that's fine. Then we can assume that you're all experts now in vector spaces, and I guess so. I mean, you have already finished assignment 2A, sorry, and we can now move then to classification. So classification is one of the main topics in machine learning. So it's a very essential aspect when we start talking about machine learning. And so today we will define what is classification and how we can represent classes in a vector space model and in general. So the concept of representing classes and membership to classes. So what does it mean for an object to be a member of a class? And then we will look at two classifiers. So we'll look at the Rocchio classifier and the K nearest neighbor. These are two simple classifiers, but sometimes very powerful. And because they are simple, they will make the task of understanding classification much easier for us. So when we talk about categorization as a task in machine learning, we could think of two things. So we can think of classification and clustering. So classification is an instance of supervised learning, which requires labeled training data. So in classification, we have labeled training data, and what we mean by that is that we have examples of the things that we want to learn. We want to learn how to classify. So we provide a classification algorithm or a model with a set of examples that we have annotated, manually annotated, and say this is what we want to learn. And so we train a classifier to automatically assign new instances, new unseen objects to predefined classes given these examples. So we'll give more concrete examples of what we mean by classification in a minute, but this is the overall definition of supervised learning in general. So supervised learning assumes the existence of labeled training data. And clustering, on the other hand, is a form of unsupervised learning. So here we don't have training data, which means that we actually don't know exactly what to expect from the model or the algorithm. So we know that we want the algorithm to return clusters, groups of things that are similar, but how many and what is the nature of this, we don't know exactly. So that's left for the clustering algorithm. But what we can do is define for example, what we mean by similarity measure. So how can you cluster? When we ask the clustering algorithm to cluster things together, it will depend on finding similarities between objects and assuming that these are clusters. Anyway, we will return to this next lecture. This is not what we are going to talk about today. So, classification. So, what's classification? So, here are some concrete examples to make you appreciate the task and maybe keep up with me until the end of the lecture, so that you see how actually useful this task of classification is. So, spam filtering is a classic textbook example of classification. You all encounter this and use it every day. So that's the spam folder in your emails. So defining whether an email or classifying whether an email is spam or not, this is a classification. So what we do usually is we train a classification model on examples of spam emails and then deploy that on some server, and that will be run together with your mail server. And whenever you receive an email, it will be classified as either spam, so if it's or not. If it's spam, it goes to your spam folder, and if not, then it's in your inbox. Named entity recognition is the task of assigning some abstract semantic concepts, if you want, to proper nouns. So if we take an example like Stefan Eupen is German and he teaches at the University of Oslo. This is a running text. This is a sentence. We want to identify what are the named entities in this sentence. So Stefan Eupen is a named entity. It's a proper noun. It's a proper noun indicating a person. Germany, Oslo. These are two cities. Those also proper nouns. We want to classify to which type of proper nouns they belong, to which type of named entities they belong. So cities. And then University of Oslo is an institution. So that's also, so this is a task of classification. Yeah, it's, did I say city? Oh, sorry. Yeah, it's of course a country. Yes, it's a place. That's what I meant to say. It's there's no arguing in that. So document topic classification is something like Google News. So if you go to Google News, you will find the news articles classified under different topics. So this news is news pieces about politics, sport, etc. Authorship attribution is identify or classifying who is the author of a document based on stylistic features or use of words, etc. And finally, sentiment analysis is classifying things that we write or utter, say, whether they are negative or positive. This is a very, very popular task in natural language processing and classification. So if a company wants to launch a new product, so maybe they launch it in some country first, and then they collect data on reviews and websites and Twitter and etc., social media, and they classify these in terms of whether the reaction was positive or negative. One example you could look up today is sentiment analysis for presidential election in the US, and you could see how people are reacting to the different presidential candidates. I guess there is a pattern here, but yeah. So today we are looking at these two, Rocchio classifier, KNN-classifier, and both are work in vector space setup in a sense. So the idea is that Rocchio and KNN could be used in some of these tasks. So they are not the best, but the simplest. So sorry, I have to turn this off. Yeah, they are the simplest of the simplest classifiers. So what do you mean by a class and classification in general? So what's a class in vector space model? So again, we said that we represent individual objects as points in our vector space, but how do we represent a class, which is a collection of objects? So in vector space models, classes would correspond to a region and within the vector space. So this two-dimensional vector space or two-dimensional plane, not the space, would have so if you think of these as documents with topics UK, China, and Kenya, you can see that there are regions within our space, and this region is what we will refer to as a class. And in vector space models, we would when we want to do classification using in vector space models, we will rely on the contiguity or contiguity hypothesis, which says that objects in the same class form a contiguous region, and regions of different classes don't overlap. So we don't expect documents of the UK to be spread all over our space. That will not work in our assumptions or in our hypothesis. And to sort of get a sense why documents belonging to the UK or talking or describing things related to the UK, China, and Kenya could be positioned in different places in the vector space, you'd think of words that can occur in these documents. So in China, you would an important feature would be Chinese, Mao, Beijing, right? So these are the words that would be dominant as features. Whereas in the UK, you can think of things like Queen, London, and so they would be positioned in different regions. And in Kenya also, Nairobi and Swahili and etc. So this is one important assumption that or hypothesis, sorry, that we will take with us in order to be able to apply classification in vector space models. And what classification really means then is how can we define the boundaries that separates the classes? So these boundaries here, they are called decision boundaries. So classification basically is how to define these boundaries. This is what we mean by classification. But defining the boundaries itself is influenced by how we choose to represent the class. So now we're talking in general that a class would be positioned within a region, but how can we represent it, as in like what vector or what mathematical representation would we give to the concept of a class? And that's something we'll discuss now. But another thing that could actually also influence the boundaries is also how we represent the objects themselves. So how we represent the documents. So the choice of data of features would also be influential in the distribution here of points. So to represent the class, there are different ways. The simplest and most straightforward way is to use so-called exemplar-based representation, which means a class is represented by every stored instance of a group of the class itself. So any document that belongs to a class, if again we're thinking document classification, any document could be representative of this class. So that's one way of thinking about it. So there is no abstraction. We can have, if we have 10 documents or 10 elements, 10 objects within our class, each of these could be a representative of the class. And this is what we sometimes refer to as instance-based or memory-based learning. KNN, K nearest neighbor, is an example of this, as we will see later. And yeah, so the class basically then is this collection of points. So this is what we define as our class in the vector space model. Another variant of this definition is the so-called medoids. So this is if you know what centroids, medoids is a wordplay on medians. So centroids is something we'll explain just now. But so medoids means that given a class with n objects or n elements, we want to find the element that's most central in this class and consider this as the representative of the class. And how do we define what's most central? Is usually done by finding the object that has maximum average similarity to all other objects in the group. So we look through all the elements within the class, we compute their similarity to all other elements, so pairwise similarity, and then we pick the object that is the most similar in terms of average similarity to other objects. And that would be our representative of the class. So this is one way of doing it. So other way is to look at centroid-based representations. So in centroid-based representations, we look at the average, at the center of mass in the region, meaning that we want to find an average of all the elements within our class and take that as our representative. So this mathematically, this could be done by given a class Ci, and where each object OI is a member of this class, which is also represented as a feature vector xj, we can compute the centroid mu as the sum of all vectors. So we sum all the feature vectors and then divide by the cardinality or the number of members within this class. So basically, as you normally compute the average, you can compute an average vector also. So sum the things you want to compute and then divide them by the total number. That would give you a vector that would what we call centroid. So now what we want to so the both centroids and medoids are representing the group by something we refer to as a prototype. So a prototype of the class could be a medoid or a centroid. But an medoid, as we explained, the medoid itself is a member of the group. So it's a document within the class of documents on the UK, for example. Whereas the centroid is an abstract prototype. So it's a new, completely new feature vector that we compute as the average of all other vectors. So it's not part of the documents. Is this clear? So we got the difference between medoids and centroids, yes. And we can talk about the notion of typicality. So when we start talking about prototypes, we can think of what is typicality. Typicality is how a member of the class, how close or how similar is it to the prototype. So we compute the distance between a member and what we take to be as our prototype within the class, and that would give us the typicality. Another variant of centroids could be distance-weighted centroids. So we can say that not all members within the class can contribute similarly or equally to computing the centroid. So, and as we will see later on, there can be documents that are, or elements within the class that are what we call outliers. So these are some kind of documents that happen to be part of the class or elements that happen to be part of a class, but they are very far from the class itself, from the region. And we don't want these to be contributing as much as the rest to the to computing the centroid. So we can introduce this concept of distance-weighted average, which again is determined by the average pairwise similarity of a point within the class to other members in the class. And this whole discussion of how to represent classes and what's typicality is existing in other fields. It comes from other fields, from linguistics, from psychology, and etc. So this concept of prototype, what's a prototype of a class, or how do we represent a class? It's traditionally in many different schools of thought would be, so defining a class would be setting a list of properties or attributes that an object should possess to be a member of this class. But in a prototype theory, we say no, there are things that are more representative, more typical. So if I ask you can you give me an example of a piece of furniture, you're more likely to say sofa and chair than telephone and or even stool. Because you think of sofa and chair as more prototypical, more typical examples of the class of furniture. So this is what we, yeah. So it's a long discussion, but it's interesting to know that it's actually related to other fields. Yeah. You don't. So when you compute the average here, you just sum them, right? So you can add a weight just before the vector, and that weight is based on how similar or dissimilar the vector we're looking at the moment from other members of the group, and that could be something between 0 and 1, for example, and then those that are very far away would get 0.1 or 0.0. So that's the idea here. Yes, so this is how we represent a class, or ways of thinking how to represent a class. But what about class membership? So here we can think of two things, or two types. So we have hard classes and soft classes. So in hard classes, membership is Boolean. So a member is either within the class, or an object, or is either a member of the class or not. So there is no graded scales here, nothing. It's either or, and this is what's also sometimes called the crisp membership function. So, and as the name suggests, it's just a hard decision saying whether it's within the class or not. A variant of this could be that an object could be a member of many different classes, but for each of these classes, still, it's a hard decision. So it's either within or not. The other way of looking at membership is soft classes. So soft classes then defines membership as a graded property. So an example could be distance weighting. So how far an object is from the prototype, and then we determine how much of a member is it within our class. And here we can think of two ways of introducing membership functions. So there is a probabilistic membership function and a fuzzy membership function. So in the probabilistic membership function, the degree of membership is going to be between in the range from 0 to 1. And so a member of so an object could be a member in a class with a probability 0.4, and it could be a member of other classes. And the important thing here is that the overall membership values should sum to 1 for one object, right? So if it's a member of class A, 0.5, then if it's member of class B, that's going to be 0.5. It can't be more than 1, otherwise it's not probabilistic. Whereas in the fuzzy definition of membership functions, still the value or the grade, if you want, of membership is between 0 and 1, but we don't have this probabilistic restriction. And this is again not very central in our curriculum, but the distinction between probabilistic and fuzzy can be sometimes difficult. So what does it mean to have probabilistic membership, and what does it mean to have fuzzy membership? So, and you can think of fuzziness and probabilisticness, I guess, in natural language. So I could say he's probably old, and I could also say he is somewhat old. In the first one, I use the adverb probably because I'm not sure. I'm not certain about the knowledge here. Maybe I have spoken with him on the phone, but I haven't seen him, so he's probably old. But in the other case, when I used the so-called hedge and like somewhat, so he's somewhat old, I know that he's old, but I'm not sure whether he falls within this class, fully falls within this class of old. So he could be old and young at the same time. So this is, you can think of probabilistic, the probabilistic sense is uncertainty about the knowledge, the information you have, and fuzziness is more like an uncertainty about the truth itself. So what's old, what's cold, what's hot, etc. So yeah, so what's a Rocchio classifier, or what's Rocchio classification? And this name Rocchio classification you will encounter in information retrieval context, because it comes from so the name comes from the person who introduced the algorithm in information retrieval. But it's also called nearest centroid classifier, or nearest prototype classifier. And what the algorithm does here is that it takes an input of training examples. So labeled objects or labeled documents with classes, and it computes the centroid to represent these classes. So it's centroid based. So for each class, we compute the centroid, again, as we defined before, based on the average of the feature vectors for the members of this class. And then when we are given an object to classify, which would be in this case represented by, say, the vector xj, we determine which centroid UI is the closest to xj. So measure the distance between all the centroids we have now in our model, and assign the class of this closest centroid to our unlabeled, unknown feature vector xj. So think of this as you have trained a model on classifying documents. Your model has 3 classes, and then now you are given a new, completely new unlabeled model. You want to predict what's the class of this not model, document. So again, we have a document classification task. We want to predict the classes of documents that were not seen. So new documents coming into the model, and then what would happen is your model would have computed already the centroids of the classes you trained on, and then it measures the distance between the feature vector of the new document with together with all the centroids, and then assign the class of the closest centroid to this new document. And these centroids, the centroids we compute, they introduce decision boundaries. So they introduce the decision boundaries, or the boundaries between the class regions. So if we look at this figure here now, so what's a decision boundary? A decision boundary is the set of points that are on equal distance between the centroids of 2 classes. So in a 2-dimensional space, the set of points would be a line. And if we have, in this example, we have points in the class UK and points in the class Kenya, and we computed the centroid here for Kenya and this centroid for UK. And the decision boundary is this line here that has, for each of all, for each point on this line, the distance is exactly the same from the centroid of Kenya to the point, and also from the centroid of UK to the point. So A2 here refers to this distance, and A1 refers to this distance, and these are exactly equal. So this is what we mean by a decision boundary. And this is the 2-dimensional representation. So in 3-dimensional space, the decision boundary would be a hyperplane, or sorry, a plane, and in higher dimensional would be a hyperplane. So it would be one thing to note here is that we don't actually or explicitly compute these decision boundaries. So these decision boundaries, they come out of our first representation of the class as a centroid, and then the rule we said that is we are going to assign the class of a new unlabeled object to be the closest centroid. So in practice, you don't compute these. What you compute in the algorithm is the centroids. But in a conceptual way, if you can think of decision boundaries like this, and they have this very clear definition as being the points in that are in unequal distance between the from the 2 centroids of the classes. So given our definition of the Rocchio classifier and the way we wanted to, or we want to represent classes, there will be some problems. So this will be immediately clear. The first thing is the way we compute centroids, we actually ignored the local distribution of the points. So we just computed the average. We didn't look at the local distribution. And then the whole algorithm is based on the centroid distance. So, and a class is represented by its centroid, and the classification is based on this centroid, is that on the distance to the centroid. So we will see a couple of examples on why this would be problematic if you don't look at the actual distribution, local distribution of points. And then the Rocchio classifier assumes that the distribution of the points in this regions that we talked about have spherical shape. So they have this spherical shape for it to work well. So in a sense, so the Rocchio classifier would have this assumption, and also assumes that classes also are of similar size. So they have the similar radii. I think this is pronounced like that. So plural of radius. So this is also another assumption made in the classifier, but this is not necessarily the case, of course, in real life. So this is going to be problematic as well. So yeah, and this falls out of what we talked about here as the assumption of classes being spherical. Means that the classifier will not work well with classes that cannot be accurately represented by a single prototype, by a single vector. And this could be disconnected classes, disconnected regions in our vector space. Again, we'll look at this in more visual examples. And this could be also the classes that are stretched out in the space. They don't form a sphere, they are stretched out. And one last thing is, and this is an important by definition, Rocchio is a classifier that defines linear decision boundaries, which means that classes that cannot be linearly separable will not work with, or Rocchio will not be able to work with. So what do we mean by linearly separable? So if you go back to this example here, so these are the points representing UK, and these are the points representing China, and we can define a linear equation or a line in this two-dimensional space, where we can draw a line that exactly separates the points of class UK and class China. So the points belonging to UK happen to be on the right side of this line, and the points belonging to China happens to be on the left side. So this is an example of linearly separable. You can define or you can find a line that separates these two classes, and then based on this line you can classify. So you input the point or the feature vector you want to classify, and see whether it falls on the right side or the left side, and decide whether it's on UK or China. Rocchio will not be able to work with classes that do not have or cannot be linearly separable. Yeah, so the concept of linear separability is actually very important. So if you have a question about that, you can. Yeah. That's the KNN. So you mean a system that's not linear or a class that's not linear? Or a system, so a classification algorithm could be could work with linearly separable classes, and some could work with non-linearly separable classes. And KNN, k-nearest neighbor, that we'll see later on, is an example of classifiers that can learn non-linearly separable classes. Exactly. So that's what we will show as a visual example, because it's much easier to look at. So, but it would be basically I'll keep this until after the break, and you will see it. So we take a 15 minutes break and then come back. Start again. Yes. So before the break, we introduced the Rocchio classifier, and we talked about the different problems that we could encounter, or Rocchio classifier can encounter, given the representation of classes. So now let's look at visual examples of how these problems here could manifest in a way in real life. So this is what we call an ideal solution or situation for Rocchio. So we have points belonging to class A, and then points B in class B, and we compute the centroid. So that's what Rocchio will do given these two sets of points. And then this would be the decision boundary. Again, it's the set of points that's on equal distance from the two centroids. So this is ideal. They both are spherical. So the two classes, they're distributed in a spherical shape, and they are roughly of the same size. So this is where Rocchio will be really good. And this is the unlabeled object that we want to predict its class. And in this case, it's clear it's going to be A. But of course, in real life, not all classes will be represented like this. So this is one case where the members of class A and B are stretched out. And if you can see, we still have the same centroids. Again, we have these points here in A, these points in B, and we compute the centroid, and it looks as if it's exactly, or not as if, it's actually in the same position. So nothing has changed about the positioning of the centroid, and nothing has changed about the decision boundary. And now given this point x here, according to the rule we introduced of computing the distance to centroids, it will be assigned to A. But that's not necessarily true, or at least from the look of it, it seems like it should be part of B. And this is why Rocchio fails now, because it ignored the distribution of the class members. So it just computed the center, and then it turned, or centroid, and it then it turned out to be the exact same centroid. So nothing has changed here, even though the whole distribution of the members of this class is completely different. Another scenario where Rocchio will fail is this non-contiguous class A. So the members are gathered in two groups, two regions within the space. And again, we only have one centroid for this, and it seems to be in the same position as the other examples. And this is an example of what we call multimodal classes or classification. So this is, you could get such kind of representation for if you were representing documents that are describing a country like Myanmar that has changed its name in the 80s from Burma. So these two sets of documents, they are positioned in different places because the name is different, but they still describe the same concept, right? The same country. And that you can't represent here, or you can't expect Rocchio to work with. Also, another example here, this class B seems to be more spread out a little bit, sort of the distance between the members is larger than A, and you would expect this X to be also classified in B, but it's actually closer to the centroid of A. So in all of these cases, it's not taking into consideration how the points are actually distributed. It's just taking the average, and that's how I'm going to represent the class. And this is where we talk about nonlinear distribution or nonlinearly separable classes. So this is an example of a class that's actually, or two classes that cannot be separated with one line. You cannot find one line that you can draw and actually separate these two classes. You need at least two lines, right? There's no way you can draw one line, and so this is non-linearly separable. And here also again, Rocchio will fail on this because it assumes to be classifying classes that are linearly separable, so that they have a line that can separate them. And this is where KNN will come into the picture, because KNN can work with non-linearly separable classes. But before we talk about that, a short comment on this concept of linear separability. So if you take this example here, we have two classes again, A and B. Their members now in one dimension, so we're working in one dimension space now. In this one dimension, the decision boundary will be a point, right? So a dot, if you want. And we can't find only one that separates the A's from the B's. But we can project these points onto a higher dimension space. So the same points of A and B could be projected on a higher dimension space, which is in this case two-dimensional space, and they become linearly separable. So for each point A from this one dimension, it had one component, and which is x. So we introduced y, and y was the value of its x squared. And then we could represent them on this two-dimensional space and introduce a line that separates them. So the idea is that you can actually transform classes that are non-linearly separable to linearly separable by projecting them on a higher dimensional space. So this is, again, this is not part of our course. So, but this is a basic, or one. So this is the basis for so-called kernel methods. So these are methods, classification methods also, that project points on higher dimensional spaces in order to be able to find a decision boundary that can separate them. Okay, so what's KNN? What's K nearest neighbor? K nearest neighbor is an example of memory-based learning, and it's a nonlinear classifier. So if you remember in the beginning, we talked about representing classes and using the members of the class itself. So we don't have a representation really. We just remember all the members of this class, and we take all of them to be potential representative of the class itself. So KNN works like this. It doesn't compute a centroid. It takes all the training examples that we feed it into the algorithm and use them to classify. And it's nonlinear because it doesn't need to draw this linear, or it doesn't need to make this linear separability assumption, as you will see now how it works. So drawing the decision boundary is not limited to linearly separable points or classes. So if this k is 1, so 1 and n, one nearest neighbor, the algorithm is about looking for the nearest point in our space and taking that to be the class of the object we want to classify. So given a document we want to classify, we look at our training data, which one of the documents in our training data is the closest in the space. It has the topic of politics, then the new document is politics. This is the 1 in n. So looking for the assign each object the class of its closest neighbor. And closest neighbor, again, I mean, this is something we talked about, how you can compute closeness, Euclidean distance, cosine similarity, etc. When we are looking at k nearest neighbor, so anything that's greater than 1, then we assign the majority class among its k nearest neighbor. So given a data point, unlabeled data point that we want to label, we look up its k nearest neighbor, so the top k nearest neighbors of the feature vector, and then find what's the majority class within the nearest neighbor, and assign that to the input feature vector or document. So the rationale here is again based on, yeah, sorry. Oh, okay, so sorry. The majority class, so if you have 10 and n, 10 nearest neighbor, you looked the 10 nearest neighbors, you found that 6 of these 10 or 7 of these 10 are assigned the class politics. And so the majority have the class politics. So it's basically just the majority. So the majority of people, the majority. So this is what we mean by majority. So 7 out of 10 is a majority. 6 out of 10 is a majority. 5 out of 10 won't be, because there might be other, not necessarily. So if another, so if we have 5 of class A and 5 of class B, then it's no longer a majority, but it's 5 of class A, 5 of, with 3 of class B and 2 of class C, then 5 is still a majority. So it's in this really basic sense of majority. That's what we mean by majority class. And so why would we expect this to work again? So what's the reason? Given this contiguity hypothesis, when we are given a test object OI, we expect it to have the same label as the training objects in the local region. So remembering this contiguity hypothesis is that the documents belonging to the same class will be in the same region. Then if we are given a new object that we want to classify, we can look at its neighborhood and assume that it has the same class of this neighborhood, or the majority of the points in the neighborhood. The parameter k, so we're talking about k, so how many in the neighborhood, that's something that we have to specify in advance. We'll look at this later on. But what's happening in KNN is that the decision boundary is determined locally, right? So we're looking at all the points within the class. Unlike Rocchio, we look at the centroid. So we look for the average, the average feature, and then take that a feature vector and take that as the representative. Here, we simply search through all the points in our training data and decide based on neighborhood within the class. So this is local. So this will look into all the points. There is no one representative of all the points. And the decision boundary here, again, conceptually would be would correspond to something called Voronoi tessellation or Voronoi diagrams. So what's Voronoi tessellation? Tessellation is basically this tiling up of space. That's what we mean by tessellation, or it's often called also Voronoi diagram. So if you have k equals 1, and for a given set of objects in the space, if we let each object define a cell consisting of all the points that are closer to that object than to other objects. So what that really means. So looking at these polygons here, so this would be a Voronoi cell, and it consists of all the points that are closer to this object here than any other object in our space or our plane. So drawing these polygons, these convex polygons, is what we call Voronoi cells, and decomposing our space into Voronoi cells is what we call as what we refer to as Voronoi tessellation. So these are representing, in a sense, also the boundaries, the decision boundaries, right? So because now we defined this cell to be all the points that are closer to the object here, right, than any other objects. So if we are given now a new document that happens to be in this cell, we know it would be of the class of the point here. So if you look, yeah. Yeah, that's a good question. That's something, so that I don't know what you would do, but so assigning an object to both classes, that would depend on how you define your classification task, right? So you could define your classification task as it allows the document or the object to belong to two classes at the same time, and then it would be fine. You say it's on the boundary, it belongs to two classes. But if you have a classification task that allows you to assign one object to one class only, then you have to make a decision, and then that's up to your implementation. And that won't be a problem, as we will see later on, that because we don't work with one neighbor. So we'll work with more than one neighbor, and then it's less likely that you will have these kind of tricky cases. But it's dependent on how you define the problem, and how then, based on your definition of the problem, how you solve this tie, if you want, or the border case. So yeah, so if we are given this star here to classify, that's our input unlabeled object. We want to assign a class to this. And one KK, and one nearest neighbor, we see that it falls within this Voronoi cell, so we will assign a circle. Whereas if we have three nearest neighbor, then it's actually this circle. That's what defines its the classes that it might belong, or the nearest neighbors, and then we see that the majority now is 2x's, so then it's this is an x. And the decision again, yeah, so what we saying here is that this, as you can see, these decision boundaries is clearly not linear, which shows that the KNN actually works in a nonlinear setup, or non-linearly separable setup. So yeah. Sorry, can you? The black, these, yeah. No, so all of these are points in our training data. And these points happen to be of class circle. These points happen to be of class X. And then the majority, yes, the majority is in this case, because there are two X's, is X. So this is what we define as a majority class. Because we have 3 points to consider, or it's 3 nearest neighbors, 2 of which are X's. Then it's of the input star here would be classified as X. One cell, the cells here is just a way a conceptual way to show the decision boundaries. So the cell is not really part of our training data in a sense. It's just it represents the decision boundaries related to this circle here, for example, to this data point here. So this whole cell is what we call, so this would be the decision boundary. Everything that falls inside this cell would be classified as a circle, given that we're working with 1 and n. Yeah, if you're working in 1 and n setup, 1 nearest neighbor. Yeah, yeah. I think so the notion of a cell is not part of how we define the classification task. The notion of a cell here, or the Voronoi cells, Voronoi tessellation, is just a visualization of the decision boundaries. So, and in a sense, the points here also they as separately they represent a class, right? So because this is how we defined our representation in KNN to be each point belonging to a circle can be a representative of the class. But the cell itself, I'm not sure if you can say that this is a representative of, so a cell cannot be a representative of a class. I mean, except in one very specific and special case where you set the k to 1, then you can broadly and not very precisely say that a cell could, a cell, actually you can say, yeah, you can say, if you have 1 and n, you can say a cell, any point within this cell will belong to the group circle. So any given point you give me, and it happens to this within this cell, I will take to be a circle of type circle. And that's where you have yes, so in a sense, yes, because then so in Rocchio we had one representative, and so we have a decision boundary per class. Here we have it per member of a class. I think that was all that I wanted to say here. Yes. So what's, yeah, sorry. Well, the actual but you basically do is they have to go through all the members within the your training data. So you visit them all, and I mean in terms of programmatically, you would have to compare with every single data point in your training set until you find the k best. How can you pick a circle, and if you have a matrix? That's, you see, I mean, this is visually, yeah, this is so simple, but in practice, unless you introduce heuristics, and in practice you would have to go through them to find the k best or the k nearest neighbor. Any other questions? Okay. So yeah. What does the decision boundary have to say with what kind of object? Or yeah, so the decision boundary is actually, so drawing the decision boundary is the classification task. So the decision boundary, it delimits the area where a point could be to be a member of a class. So no, that's just to show that it's we're looking at 3 nearest neighbor. So and so the example of 1 nearest neighbor and then 3 but it's not a boundary in this case. Decision boundary. But for other, so for the if you look here, then the decision boundary refers to or to classification. So if a point happens to be within the cell and you are looking at the 1 nearest neighbor, then you could see that it's within this boundary, and then it's of this type of a class. But then again, I'm trying to show this as a visualization of the decision boundaries. We don't compute the decision boundaries in essence. What we compute is the distance to the points. It's just a visualization of how these decision boundaries would be drawn.
One could maybe say that the decision boundaries here show the neighborhoods that falls into one of the areas of the cells, all points within those areas will be considered the nearest neighbor of the
Yeah.
instance in that cell. So they define, in a sense, neighborhoods. One best neighborhood.
Yeah.
One nearest neighborhoods.
And the one best neighborhood then would define the class of the input object.
So if you think of, you always do shopping at the closest grocery store, then you could draw similar cells across the map of Oslo for each street address. That would be the cell for which one grocery store is the closest.
Yeah. It's, so the k here is one thing that we need to specify. So what's the value of k? So if we take k to be only 1, then we end up with something like this. So we have a very fine-grained and very specialized classifier that is probably not the best performing for us. So if you look at the blue and yellow, I guess this is yellow, circles here, these circles here could be the blue that are within the yellow, could be noise, could be mistakes, could be outliers of the blue. So only looking at one nearest neighbor might not give you the best result. This will give you a very specific and very fine-grained decision boundary. Whereas if you include 15, you would have a much smoother decision boundary. So if you look at 15 nearest neighbors, and it's still nonlinear, of course, but this seems to be capturing the regions of the two different classes. So with smaller k's, you would have a very specialized and this kind of what we call islands here. With bigger ones, you would have smoother, but what would happen if we take our k to be the same number of the training examples we have? What would be the result? So for each document or object we want to classify, we consider the k nearest neighbor to be all the training documents, all the labeled documents, labeled objects we have. What would be the result? One class, yes, but what is that one class? Yeah, or yeah, but still, I mean, there is a property about this class and you will always get this class. Exactly. So it's the majority class. So if one of you, and that's often the case, is that the distribution of the training examples is not they are not equally distributed among the classes you want to learn, then the looking at all the documents will always give you the most common one, right? So whatever document you input, whatever object, you will always get the majority class of your training set. So yeah. So normally choosing k is a matter of sometimes trial and error, sometimes as you make judgments. But one thing also you should consider is not the so if you have 4, you might get a tie. So maybe you want to use odd number of nearest neighbors. So then you 3. So odd number means that there will be a majority. So other versions of the k nearest neighbor classification, which makes the algorithm even more, or make it more robust. Yeah. Well, that's so what when you normally train a classifier, you would have this is something I'll jump a little bit ahead and then come back. So we have been talking a lot or we have been talking only about training data, but in a normal life scenarios, you would have training data, test data, and maybe development data. So, and the idea is that you usually train on this on your training data, and then try your model on your dev data. You don't touch the test data. It's something that we will talk about later on, and you try with Ks. So that's one way of trying to figure which K is best for you. But with one you will get these. So if you have, especially if you have noisy examples like here. Yeah, to me at least, I don't know if there are any heuristics. I don't know. Are there any heuristics on the K? Maybe related to the number of classes. But to me, it has been always a matter of learning this K, how many you actually need for your application. That's how we define a K. So to make the algorithm a bit more robust, or give it a bit of variation, so we can introduce the probabilities or probabilistic membership into the KNN, meaning that when we are in this example looking at the 5 nearest neighbors, we're given X. This is what we want to classify. And we find that it's in its 5 nearest neighbor there are 3 A's and 2 B's. So we can assign a probability to to X being of class A based on the proportion of A's within the K nearest neighbor. So and the same for B. So in this example, X would be a member of class B with a probability 0.4 and a member of class A with a probability 0.6. Because we have seen we have seen 5 nearest neighbors. 3 of them are in A, 2 of them in B. We don't want to make a decision. We want to give probabilities. It's this much. Yeah. Very good. That's what we are going to talk about next. That's you're one step ahead. But that's, yeah, so this is how we, given the probabilistic sense of membership or class membership, this is how you would compute that in a KNN classifier. When it comes to, so as you just said, there's this interesting observation here, is that even though we have only 2 B's and 3 A's, the B's are actually very close to the X. So maybe we should take the distance also into consideration when we want to classify this X here. So we could measure the so what we would do is again find the 5 nearest neighbors and then measure the similarity between the X and the vectors in B and X and vectors in A, and then score the class A and class B based on these similarities. So this is done as here. So it's simple. So what you do is measure similarity between for class A, go through the K nearest neighbors. If the vector xn within the K nearest neighbor of belongs to class A, then this I here would be 1. And then you multiply that with the similarity between xn and xj. Xj is what we want to classify. Sum these, and that would be the score of oj, the object we want to classify, being of class I. And then do the same for A. So if go through the K nearest neighbors, if the vector we're looking at now is of class A, then this would be I. If it's of class B, then this would be 0. And multiply that by the similarity, and then score them and see which one is scoring higher, and that would be the class of B. Is this clear? Yeah. So this would not only give you better results, it's actually then this would help you solve the ties we talked about. So how many? So if you have 4 Ks, that would introduce a tie. But now you have this sense of similarity and scoring, so you can skip over worrying on how to resolve ties. Yeah. So why do we need this? So in order to be able to write this formula, really we needed to introduce this I, meaning that what the sum here loops through all the nearest neighbors, right? We are computing the score of class A. So, but the nearest neighbors include feature vectors of class B as well, right? So when they are of different, when the vector is of a class B, then I would be 0 because we don't want to compute that into the sum for class A. So it's just that given a class Ci here, if the vector we're looking at now belongs to this class Ci, then I here would be 1. If it belongs to some other class, so that's 0. So it's just to compute the score. It's no, this is not the object we want to classify. Xn is part of our training data, so we know to which class it belongs. Xj is what we want to classify. I could just drop this I here and then add a condition that so xn belongs to the k nearest neighbor and is of class, say, Ci. It's just a way of writing it. And yes, so I found, yeah, so I can explain the notation here. So O is the word itself, or the object J that we want to classify, and Xj is the feature vector of that object Oj that we want to classify. This might be a bit yeah, sorry about that's yeah, so this this actually happens several times in the slides. So you would see we talk about an object J, but the way we represent it with a feature Xj. That's what you were asking about, right? Yeah. Yeah. And that score is computed based on the similarity, and similarity could be computed using one of the measures we introduced, like Euclidean similarity or cosine similarity. But of course, when we say A and B here, why we compute their scores? Because we know they occur in the neighborhood of the object we want to classify. So we don't do that with all the classes, right? So it's so some peculiarities of K nearest neighbor. So as you can tell, there's actually no learning happening here. So we're given a set of examples, and then we just compare with these examples and look for nearest neighbors. So we are memorizing the training examples, and that's what we refer to as instance-based learning or memory-based learning. And in generally speaking, very generally, it's the more training data you have in machine learning, the better. And KNN, that's not necessarily the case, because since we are comparing with all the training examples, once the training set gets larger and larger, the efficiency will be worse and worse. So again, comparing, so the test time, or so it's the test time is meant by test time here is that comparing with all the vectors or the training examples is linear to the size of the training set. So if our training set has 10,000 documents, then we are going to do 10,000 comparisons. But the number of classes, So it doesn't matter how many classes are there. So, so 10,000 documents could have 2 classes and could have 900 classes. That doesn't play a role in our setup, and this could be potentially advantage. And so you could think of this as an advantage for KNN, is that it doesn't depend on the number of classes. And lastly, you can. So since we talked about this information retrieval and search engines, etc., there is this similarity between using KNN and looking for relevant or similar documents within the search space and information retrieval. It's basically both of these are looking for the nearest neighbor. So when you have a query, you're looking for the nearest neighbor within the nearest neighbor for the relevant documents. This is not especially important. It's just to realize the similarities here. Yeah, so maybe I could say a few words about obligatory assignment 2B, which was published yesterday. So we in 2A we represented, or we built a vector space representation of a set of words, this 122 words that we gave you, based on bag of word features extracted from the Brown corpus. In 2B, you will be reusing the same thing, so it builds on top of 2A, and we're still using vector space models, and you're still using the same files, Brown corpus and words, but now we provide you with class labels for these words. So not all of them, so some of them will be given classes, or you can think of these classes as general semantic concepts. So the label for potato and food and bread and fish and eggs, etc. This is food, and these are so embassy, institute, college, government, institution, etc. And then some of these words in the class would be labeled unknown, and that's what we want you to classify. So we want you to learn the classification of the words that are unknown. So, we want you to build first train a Rocchio classifier to predict the labels on for these words that are unknown. We don't know the classes of these words, and the task is to learn to build a Rocchio classifier, basically computing centroids for all the classes, right? So as we explained today, all the classes that are provided here, you look up their members, and then you compute a centroid for that, and then when you have an unknown word, you measure the distance to these centroids and assign the class of the closest centroid to the unknown word. This is due in 2 weeks, and you can use. So we will publish the code for 2A, which you can reuse, since we're going to build on 2A. So to assume that all of you have the same starting point, so we provide the code for representing vector spaces and etc., which is a model solution basically for 2.1 or 2A. And you can also, you're free to reuse your own code. But yeah, too much about the assignment. You can read the text. I was actually planning to go through testing of classification and how we test the classifier. So not sure we have enough time. So just quickly, very quickly, and we'll come back to this, is that we defined vector space classification as as basically drawing the boundaries, right? Drawing the boundaries between the classes. And there's an infinite number of the ways we can draw these boundaries or decision boundaries. How can we objectively decide which is the best decision boundary? How can we evaluate a decision boundary? That's something we can do through measuring the number of correct classification prediction on unseen test items. So as I mentioned, we have been talking only about training data, but usually in normal setups you have a training set and a test set. And the test set is meant to be held out. So if you don't look at this, you don't use it, and it's meant to be representative of the training data, and it has things that you have of course not seen before, or your model has not seen before, and it's used to measure how your model can, whether it can generalize on new unseen objects or not. Well, there are many ways to compute this, and I guess we will just have to stop here because time is over. I'll return to this topic in the next lecture before we start with clustering. Thank you.